Hello everyone, today I'm thrilled to share with you the journey of my special project in electrical engineering. The topic might sound a bit technical, but it's something fascinating. It's circuit logic optimization using the Quine-McCluskey method. Before we dive in, let me introduce myself. I'm Pan Yanxi, and this project was guided by my professor Liu建-nan. Here is the outline of my presentation. The first is an introduction to the Quine-McCluskey method, the task of optimizing the logic in Verilog design file, the code demonstration and the implementation process, and the results of check equivalence and gate counts reduction. And also, we'll talk about future improvements as well. So, what exactly is the Quine-McCluskey method? To put it simply, it's a way to minimize Boolean functions. Think of it as similar to the kernel map, but instead of using a visual grid. It uses a tabular form, making it much easier to implement in a program like C++. Of course, there's a catch. This method has a major drawback. Its runtime grows exponentially as the number of variables increases. Now, let me take you through how I implemented the Quine-McCluskey method. First, the process begins by identifying all the implicants in a given logic function. Then I checked if this implicant could be merged. Once no further merging was possible, the remaining implicants became what we call prime implicants. From there, I created a truth table that records these prime implicants and extracted only the ones we need, and it is called the onset. But implementing the method was just one part of the project. The real challenge was applying it to optimize logic in Verilog design files. Let me explain how I tackled this step by step. To start, I needed to build a circuit graph. Ideally, this would be done using an adjacency list or a directed acyclic graph. However, due to some oversights, I ended up using a binary tree instead. Thankfully, this approach worked because the gates in our design were restricted to just two inputs. By connecting wires, inputs, and outputs to nodes in the tree, I was able to build the structure for the circuit. And if the node has already been recorded, there's no need to add a new node and just point the node to the existing one. Next, I constructed a truth table. This part involved passing the root node of the tree into a calculation function. The function processed all the inputs and applied logic gates to generate the truth table. I used these two functions to build the truth table, namely calc output and calc gate. And let's start with calc output function. Its purpose is to recursively compute the output of the logic circuit. It checks the current node type to decide whether to directly return an input value or to further process the left and right child nodes. For single input gates such as NOT or buffer, it calls the calcgate function with appropriate parameters. And the next is calcgate function. It handles the logic operations of various gates like AND or exclusive or some more complex types such as NAND or NOR. The logic of this function is just performs Boolean operations based on the specified gate type. And if there's unsupported gate type encountered, it will return an error message to ensure that program is correct. Finally, I applied the Quine-McCluskey method to minimize the Boolean function. The process involved comparing rows in the truth table, merging rows with minimal differences, and replacing bits with dashes where merging occurred. This continued until all the essential implicants were identified. The result was then returned to a blip file for verification. Now let's talk about the results. I verified the output by checking the circuit equivalence between the reference blip file and the truth table from a program. Most of the test cases passed successfully, but there were a couple that required such long runtimes that I couldn't obtain the results. On the bright side, the optimization significantly reduced the number of AND gates by 30 to 80%. This kind of reduction is crucial for lowering manufacturing costs in circuit design. However, the project wasn't without its challenges. The most significant issue was the long runtime of the Quine-McCluskey method, especially as the number of inputs increased. Moving forward, I plan to address this by using faster data structures like unordered maps to handle the truth table. I also aim to explore parallel processing to break down computations into smaller tasks, which should speed things up considerably. To wrap up, this project has been a rewarding experience. It has shown me the potential of applying theoretical methods to real-world problems. Even when they come with challenges, I'd like to express my deepest gratitude to my professor and to my friends who supported and guided me along the way. Thank you all for listening.